emergency service priority. This one is some image of a control center with the visual wall, with the operator console, with data center, with IT infrastructure. We have done some project in some city, but in some cities the most big question for the traffic control center is it's located in the DOT or it belongs to the traffic police. It's very big question to conduct the ITS in the urban area in Vietnam now. Here we recommended to divide the service. Which one is belong to the traffic police, which one is belong to DOT, and how to work together among the functions. We have to setting up the control center, of course, with the traffic monitoring, with detecting violent vehicle and some other service like that. About the public transport, so besides some service like the mass information system, like the stop showing about or something. So one very important thing is the integrated ticketing system for public transport. Now it's a very big question in Hanoi right now, because now we have early bus system, but we already introduced BRT. But BRT in Hanoi now we don't have a ticket system. We still using the paper. It's not BRT. So it's some next year we will have LRT, we will have metro, and one of the challenges of Hanoi now is how to conduct an integrated ticketing system. With one unique ticket, we can travel for every public transport system. For the progress, Hanoi they already issued the technical framework for electronic ticketing system, and Ho Chi Minh is now preparing for the technical framework. I extract from the framework of Hanoi some information about the technical requirement like that. So for the physical requirement for data interface, for speed of communication, for security, and for other. So every ticket that introduced in Hanoi have to follow this box. Next one is about the automatic vehicle location and dispatch. Now in Hanoi, when an accident is happened, so people have to go to 113 for police, 114 for firefighting men, or 115 for hospital. But we don't need a unique system in the emergency case, so we have to introduce this one. So with this part, automatic vehicle location, we can make the citizen support tool for the dispatch or responder. We can multiply dispatching mode, and we can do we do need also the roadside parking management system. You can see here how the system is work. And we do need also the traffic enforcement system. By the red light camera, by traffic sanction enforcement, by land use enforcement, and by speed camera. This one is red light camera, how it works. This one is traffic sanction enforcement by CCTV solution. This one is how to do the land use enforcement by radar detector and ANPR. And this one is how to make the traffic enforcement by a mobile speed camera. They bring the speed camera, the mobile ones in the roadside, and they catch vehicle upload our speed. This one is fixed speed camera. For location, so we come up with 5 solutions. Firstly, that integrate the traffic management system. Second one, that's public transport support system, and we focus on smart car for public transport. We have to do traffic enforcement system, public and civic management system, and automatic vehicle location. And not only the ITS for one or for a city, we have to focus also a smart government, smart electronics, smart environment, and everything will be smart to have a smart city. That's our purpose for the next generation of our life. Thank you.
First of all, thank you for having me today. I'm going to talk about freeway weaving management, the CITS approach, a cooperative ITS approach. Often you know that in motorways, when we have congestions, there are a couple of bottlenecks that we can get, such as lane drops. When you have a section of a motorway is going from 4 lanes to 3 lanes, or 2 lanes to 1 lane, or in an on-ramp situation where vehicles coming from on-ramps merging into the motorways, or you have a sag section where there's a gradual increase of the gradient, or a weaving section where you have on-ramps and off-ramps into weaving on motorways. Just like this example here showed that you know, on the motorways where you have a 3-lane to a 2-lane, this is driving on the left side. So the vehicles on the left side will have to merge inside, right? So most of the people, what happens in such a situation is that they will wait until they're very close to the lane drop section, and then they will change lanes. So there are lots of perturbations around that area, and that will cause a drop in capacity, you know, a flow breakdown. Another possible situation would be when you have an on-ramp and off-ramp situation, where you have vehicles coming in from on-ramps trying to get onto motorways, and then those trying to get off the motorways. And often what happens is that most people will do this, execute this movement within 100-150 meters at the merge point. So this creates a very high concentration of lane changes, and that actually reduces the speed of the vehicles. Just like what happened illustrated in this diagram here. On the left side, you can see that there's a high concentration of the movements, but the weaving section is designed for quite a long section, and the remainder of the section is actually not very well utilized. So we have an infrastructure that is designed for much longer, but drivers, by our human nature, we are very anxious trying to get on or get off the motorways. So we tend to execute our maneuvers in a very short section. So I'm just going to show you a short clip here. If I can edit. So you can see that you can see that the merge point. Anyway, you can see that the merge point is at the end of the yellow line, but the whole section is actually much longer. But most vehicles will actually try and get on and get off, try to merge, try to change lanes as quickly as possible. Right? So and that creates as lots of lane changes and also speed reduction. So to address this problem, what people I was just referring to this section here. So most people will just come in and change lane as quickly as possible, where they could have moved forward further and to change lane. So in the motorways management systems, quite often what has been used is ramp metering. So where you meter the vehicles coming in. I'll show you some diagrams, and also variable speed limit, or a combination of ramp metering and variable speed limit. So ramp metering is the situation where you have motorways, main line running like this, and you have an on-ramps, vehicles trying to get onto the on-ramps. So what you tend to do is that you install a signal at the on-ramps so that you actually regulate the amount of vehicles coming onto the motorways. So if you don't regulate, what happens is that there will be an influx of vehicles coming into the motorways and create some disturbances, right? And that will create a capacity drop and causes congestion. So this is one of the very common measures. Another one could be using variable speed limit. I know Mr. Trump here is very interested in VSL. So the idea here is that you can actually, so normally, for example, if this motorway is running 100 kilometers per hour, what you could do is that you could actually reduce the speed, so that kind of decreases the density, that would make lane changing easier. Okay, so then you allow more people to be able to change lane rather because they are coming in at lower speed, so that they still can change lane over here. The measures that I've been talking about, either lane metering or variable speed limit, the way we control it is because we are controlling all the vehicles in general. Just like VSL, we are providing information, advising drivers to reduce speed, but we're not actually tailoring the information to individual drivers. But in the future, that's quite possible with cooperative ITS, cooperative intelligence system. What it means is that we have the ability to communicate between vehicle and infrastructure, vehicle to vehicles, or vehicles to anything really. So some of the examples of vehicle to infrastructure would be signal phasing and timing advice, telling the vehicles when the lights are going to change to green or to red. Also some drivers' safety support, decision support system. So if we were to take advantage of such a measure of cooperative ITS, that is, if we can provide individual information to all the drivers, what could we do differently? So this is what we were thinking. We were thinking that if I can tell each individual drivers what to do, perhaps we could tell them way to change lane. Right? Instead of everybody changing lane in this section, you could say that the drivers number 1, you could change lane over here. Drivers number 2, you could change lane over here. So what happens is that we are distributing the lane changes along the whole weaving section. So the concept goes a bit like that. So when you're driving in the car, you're about to, in this case we're showing if you're about to go from on-ramps to motorways. And as you go along, we will divide the motorways into sections, into sections. And let's say you are the yellow vehicles coming in, right? So there's a roadside unit here for communication. As you're coming in, you will be assigned a place to change lane. So in your case, you might say, okay, well, you will be changing lane at 200 meters downstream. Okay, so that's what you do, and what this driver will do is that you drive, and as it gets to the location of 200 meters, another advice would be, another information will advise drivers to seek the right gap to change lane. Okay, so then you look for a gap to change lane, and you can see the yellow vehicles, you try to get into the motorways. Okay, and then you finish executing this scope. So the question, I suppose the research question here then would be, because the traffic flow is very dynamic, right? So the amount of on-ramps, the traffic from freeway to motorways, traffic volume, so trying to get off the motorways, they're always changing. So because they're changing, we do not know exactly how to distribute the vehicles. So we need to do some kind of optimization. So this is what the whole purpose of this research was, to find an optimal distribution. Okay? And we did that using particle storm optimization algorithm. So what we did was we created a traffic simulation model, just like the figure that we show here, 400 meters weaving section, three lanes and one auxiliary lane. And we divided the weaving sections into 8 because 400 meters divided by 8 is just 50 meters per section. And then we try to minimize, we try to maximize the flow of, we try to maximize the speed of the vehicles on lane 3 and also on the auxiliary lane. So what we believe is that if there is no certain drop in the speed, you could get probably a safer traffic flow. The objective function that we had at the time was that we're trying to maximize the speed, and we also imposed a penalty for people who miss the turn. So obviously we want to make sure that everybody is able to execute the move that they want to. This is just to show some of the demand settings that we have. This is ramp to freeway, freeway to ramp, freeway to freeway, total weaving section. So that we have different ratios, weaving ratios of 0.3, 0.4, and so forth, like that. So basically this would be this divided by this. This is just an example of demand. Actually, the later results you see, we have a much more extensive demand pattern. So if we were to do that, this is what we'll show you, the results on the auxiliary lane. This is the one that you come in from the on-ramp. So in a base case situation where you don't distribute the lane, most drivers would, as you know, they would try and change lane, and that would cause, because there are lots of people trying to change lane, it would cause a speed drop like that, very sharp speed drop. But once they pass to that merge point, about 100 or so meters, they can start to speed up to 100 kilometers per hour again. But if you were to distribute the lane distribution, lane changes, then you get a much smoother traffic flow rather than having a very sharp drop on the auxiliary lane. So if you look at the leftmost lane, this is driving on the left, by the way, which is the opposite side of what you're driving. Again, you can get similar results. So vehicles would be normally coming at 100 kilometers per hour. They'll have to drop to about 50, and then once they pass that bottleneck, then they can speed up again. But if you were to distribute the lane changes, again, you can get a much smoother speed curve here. But this is also partly because the speed is what we are optimizing as well. Now, if you look at the speed contour, the way to read this is that this is time, and this is distance from the merge point. The 0 is the merge point. This is upstream of the merge point, downstream of the merge point. The column on the left here, they are for the base case situation. The dark color, the shadings shows the speed variation. So the darker the color, the lower the speed. But what you see is that when you have a very high weaving ratio, where you have very high on-ramps to freeway, you would have a very low speed at that section. But once you pass that point, everybody is going very fast again. In contrast, when you have an optimized situation, you can see that there's no very dark band around here. Okay? So the speed are better distributed. And this is for the auxiliary lane. Now, if you look at the lane number 3, again, you get the same story, right? When you have a lot of ramp to freeway, you get very sharp drop in speed, less distinct drop in speed when you have lower ramp to freeway volumes, but kind of very gradual changes in speed in the optimized case. Now, if you look at the delay comparison, we are looking at one particular case. So in the base case versus the optimized case, the improvement from base case, depending on the situations, then the flow of movements, you could get an improvement of 30% to ramp because it's a very low volume to only 1%. So on average, you get about 28% improvements. This is what we observe. Okay, so meaning that we can actually get quite significant improvements if we were to distribute the lane changes. This is another way of looking at the average travel time. So you can see that in the base case situation versus the on the x-axis you have the ramp to freeway ratio, and then your delay improvements is greater when the ramp to freeway is very high. Okay? So if we this is a case where we did many more cases of the demand situation. And looking at the base case for the freeway to ramp situation, you can see that most people will just try and, in terms of the section, so this is 50 meter section, 100 meter section. So most people will try and change lane, the 80-90% will change lane in the first 100-150 meters. Right? Again, from the ramp to freeway, so again, most people will try and execute the lane changes as quickly as possible in the base case situation. Now, this is another way of looking at the diagram. So we have different scenarios. This is the distance from the merge point in terms of percentage. So you can see most people so where am I? I'm lost. Okay. So this is the ramp to freeway to ramp and ramp to freeway. Everybody tries to get on or off as quickly as possible. Now, if you look at the optimized case, you can see that there's, depending on the conditions, the distributions are a little bit more gradual. Okay, so this is for the freeway to ramp, and then from ramp to freeway. You can see that the ramp to freeway comes on much later compared to the base case. But if I put the two together, you see that in the optimized case for freeway to ramp, the freeway to ramp would, in the optimal situation, would be the freeway to ramp would change lanes quicker, the ramp to freeway much later. Okay, so in other words, what it means is that you try to let the people from the freeway get off first, and then you let the people from the ramp get on. Okay, that's the kind of logic to the distribution. So if you look at the speed profile, again, the base case you can see for all the cases that we have simulated, you can see a very sharp drop. Again, that depends on the amount of ramp to freeway and also the ramp to freeway volumes. So the greater the ramp to freeway volumes, the sharper the speed goes. But then you can actually optimize it in a very make sure that the transition, the speed is very low. So, in conclusion, I'd like to say that CITS advisory control strategy, in this simulated case, it has shown that it can help in improving the performance of the motorways weaving area. The same thing we can apply to a land drop situation, by the way. The same concept that if you can advise people where to change lane, depending on the traffic conditions, you can get much better improvement. I guess the real test will be, the question would be whether drivers will actually believe in such information and whether they will follow such information. That's something to be tested. With that, I'd like to end my presentation. Thank you.
Useful presentation on strategy to combine between VSL and RAM management. I think this is a very innovative strategy, and you suggest a model which the on-ramp and off-ramp location where it is very close to each other, and so the merging vehicle and the lane changing vehicle maybe interact with each other. Following maybe you have some algorithm to deal with this situation. You assume that the vehicle can interact with roadside devices. Okay, so in case not all the vehicle in the main line stream do not have cannot interact with roadside vehicle, how can we get appropriate notification for the driver to choose the best location to changing lane? Thank you.
So that's a very good question. So we did some simulation, assuming that certain percentage of vehicles can have the information. Okay? So those we found access to, those we cannot communicate, then we can provide the information. That means that they will tend to change lane whenever they want to. But what we found is that to get the impact, you need to have certain percentage of the vehicles that you can talk to. Right? What we found is that about when you get about 20% of the vehicles that you can talk to, this is where you start to get some benefits. And then you start getting benefits as you have more, you start getting more and more benefits. But the benefit doesn't increase linearly. Up to, I can't remember the exact number, maybe about 60 or so percent, that's where it starts to taper off. Then you don't get so much benefit anymore. So that's why we
So I mentioned about how we modify the algorithm. Because when, for instance, given that only 20% of vehicle can have V2I technology, and so how you can provide the useful information on the gap or the time of lane changing.
Okay.
Yes.
So obviously one of the assumptions here, in fact the very basic assumption here is that we know which vehicles is going to go to the on-ramps, from going to on-ramp to the freeway, which vehicles is going from the freeway to the off-ramp, and which vehicles are going from freeway to freeway. So we assume these movements we know, who are doing that, right? Therefore, we can target them. Now, so this is a very basic. This is a very basic assumption. I mean, I don't think it's a very unreasonable assumption because most of the people would be using a navigation tool in a car. Right? So you program, say, okay, I'm going to go A to B, and then you follow some routes, and then you take it, recommending that you've got to take this off ramp or take this on ramp. So I don't think that assumption is that bad. Now, because you know each individual vehicles what movements they're going to make, then therefore you can actually recommend those people whom you can talk to make those. Right. But of course, the solutions is not the same for every penetration rate. As in, if you have 20%,
it will depend on the penetration rate.
Yeah.
Thank you.
Okay, good afternoon. So my name is QUČC from the IT Center of the University of Tokyo. So today, I'd like to talk about the title of the practical research on implementation of ITS in local area. So this is the content of my presentations. So my interest is the implementation of the ITS in the real world. So that this is an example of the implementation example, field operational test example in Kasuga City. So Kasuga City is one of the leading city in Japan regarding the ITS. So that, and our university have, Kasuga City and our university have a collaboration regarding the ITS field. So that this time, we conducted the public transit provision of the operating information on public transit in Kasuga City. And so, first of all, I'd like to talk about the situation of the public transit in Japan. So, actually, in Japan, there are three major metropolitan areas, such as Tokyo, Osaka, and Nagoya City. These three major metropolitan areas has a share of the transportation mode of the public transit is account for the 30%, which is a little high compared to the other cities in the world. And compared to the local area, the local cities, just less than the 10%, very low level of the share of the public transit, including the bus transit and also the railways and so on. So this is one of the problems. And then, as a bus operator, operators, 70% of the private bus operators and 90% of public bus operators are actually the defective balance. So it is very severe condition of the business. And also decreasing the number of the passengers carried by the bus transit, especially in rural area or local areas. So that actually there is a negative circle in local areas regarding the bus transit, especially the bus transit. So first of all, actually in Japan, the depopulation and aging is one of the very serious issues in Japan. It's really difficult in the Vietnam situations. And then, so that decrease the passenger of the bus transit, and then so decrease the revenue of the bus operator. So that decrease the frequency of the bus systems, so that it becomes the worst of the services, and then decrease the passenger of the buses. This is a negative circle in local area. And then finally, so abolition of the bus systems. So that we have to cut off the negative circle. So one of the solutions is improve the user services by using the information communication technology, such as bus locations information and arrival time estimation information, and the transportation exchanges information. For example, the exchange from bus to the railways or light rail transit and so on. And then, if we improve user services, so increase the passenger of the buses and increase the revenue of the bus operators, and then increase the frequency of the bus systems, so improve the bus services. So that increase the passengers of the buses, so that we can cut the negative circles of the bus systems, so that our interest is improve the user services, especially using the information communication technologies. So I'd like to talk about the Kashima cities. So Kashima City is one of the bedtown cities, the suburb of Tokyo. So around 100,000 populations, and around 25 kilometers far from the center of Tokyo, around 30 minutes by train. It takes about 30 minutes by train. And many research organizations are located, especially including our university. And also the Kashima IT's Promotion Council, so I talked about later, is established by the Kashima City and University of Tokyo, and also the private companies. So this is I'd like to talk about the Kashima IT's Promotion Council. It's one of the council established in the December 2009, and we have 5 working groups such as planning and transportation information utilization and so on. And each working group has a chairman, and this chairman were involved in almost the University of Tokyo's professors. And 46 bodies members involved. So this council is organized by the academia, including the University of Tokyo, and the private sector and public sector. Private sector is for example, the bus operator or some kind of the consultant companies and so on. And the public sector, such as government organizations such as transportation, and also the police agency and the Kasuga city and so on. And so let's move on to the FOT, field operational test at Kasuga stations. So we conducted providing operating information on railway and the bus at Kasuga station. The operation information means the timetable and the train and the bus location information. This information is real-time information. And also the information provision by digital signage or electric signage or smartphone. And this FOT were conducted around 3 months. And the responsible organizer is the Kasuga City and the University of Tokyo, and the cooperation with Japan Railway East and Tobu Railway and Tobu Bus and Bamboo Bus and so on. And so, at the FOT, we create a new application for smartphone, the public transit operation information collaboration for this this FOTs. This application is provided by Apple Store, no charge. But but this time we can't get this one. So this is an example of the smartphone displays. So sorry, it's Japanese. The operating information, operation as usual, or delay information. Delay information. This means that 1 minute delay compared to the timetable. And also this is a train location system. So this is a real-time location of the trains, and these are the stations. Okay. And also this is bus information. One is information of the bus arrival, bus departures. This information is arrival and the departure information. This is the waiting of the departure. And this information is the location of the bus stops. So Kasuga City, this is the Kasuga City. Kasuga City is one of the big city. Kasuga Station is a big station, so that a lot number of the bus stops. There are a lot of many amount of the bus stops are located around Kasuga Station. And also we provide the timetable. It's a stable information. And also we install the digital signage like that. We install this digital signage in front of the Kasuga station. And this is display examples. And this information is bus arrival and departure. So this is waiting for the departure. This information is the arrival soon. And the bus location informations and railway operation information. And for this FOT, for conducting the FOT, we provide, we collect the correct operating information gathered by railway and bus operators at the server, so that actually the bus operator and the railway operator has already have some information systems. So they are already they have, and this is the bus operators systems. This is one of the bus location systems. And also the railway operator also have their own systems. And then we connect these information, and we collect this information to the server, and via the internet we provide this information through the digital signage or smartphone. And this is one of the results of the evaluations. The many users feel the services merit, and they hope the service will continue to be enhanced. And also they will have the opportunity for use and bus railways. And so this is the challenges. One of the challenges is need a business model for operating information collaboration of public transit. So this FOT's importance is one of the importance of this FOT is collaboration with the bus operator and railway operator, the different operators collaboration. But one of the problem is the interoperability of these data between the other different bodies. And we have to make the framework and conduct data structure, the cost responsibility, and also the data format security and so on. And also the expansion of the services and the verifications effect we have to. And then, so after the field operational test on the customer stations, this is the FOTs. And then, so next year, the GIAO East does provide the information. At that time, the Joban line they installed, and then after that, the Keihin-Toku line and station facilities information and so on. And the next year, the 2015, they provide, they conduct the field operational test at the Tokyo station, the very big station, and the THÜO line. Not only the bus information, but also the taxi and rental bicycle and the subways and so on. And then, so the GIAO East will expand the information provisions for the 17 lines in the March 2016. And this is a reference. So after the field operational test, the GIAO East, Japan Railways East, may create the application, GIAO East applications. So this is providing information on train operations and station facilities and commercial facilities in stations. So this is a displayed example. This is the information of the station information, and this is train locations information. And also this is each car's information. The number is the car numbers, and this information is degrees of the trains inside. And this figure shows that the congestion rate of each cars. This information is almost real-time information. Okay, so this is the image of the direction of information provision on the public transit in the future. So most of the people want to go to from the origin place to destination, such as stations, airport, hospitals, and public facilities, and so on. And they will use not only the bus, but railway, but also the other transportation mode. And also, if we add real-time operation information and time required estimation information, and we can search and reservation using ICTs, so such as Google Maps or so on. Almost we realize these facilities, but especially, for example, feeder transport stations. This time we have a few informations, and so that regarding the transit, not only the train and the bus, but also the various local transit. For example, the on-demand transit or community-based transit. It is one of the circle bus transit or so on. So that the mechanism that each people can find the appropriate transportation mode is needed, I think. So to realize society, we support safe, secure, comfort, and seamless transportation for various people with no dependence on transport mode, we think. So that we have to try to find the multimodal transit mode to find appropriate mode to find go to our destinations. So okay, let's say the conclusion. Okay, the population that aging on local area causes a negative spiral of the bus systems, and they conducted a field operational test at the customer stations, and provide information the bus and trains departures, location, and other contents, and so on. And many users hope these services will continue to be enhanced, and it is important to realize a society which supports safe, secure, comfort, and seamless transit for various peoples. Okay, thank you for your kindness, kind attention.
Good afternoon, ladies and gentlemen. My name is Huyền from University of Transport and Communications. Today, it is my great pleasure to be invited here today to make a presentation about some applications of transport modeling and simulation in Vietnam. In fact, we come from the section of transport planning and management, and also we come from the consulting center for transport development. It is the reason why we have worked a lot in transport management sections. Then Okay, here just some introduction about our organization. We are the academic one, and we also have the consulting center. We also have the company who work in the same under the same organization with the same team. We work a lot with the training, with the publication, and also with the international and domestic research. We have some cooperation with Japan, like Hiroshima University or Tokyo and so on. We also have worked with some GIAO funded projects and some other company like QUČC or MINH at the same time. And our major fields related to transport planning, the management, transport management, modeling, simulation, traffic control, and so on. Also, some project related to the ITS system. So here are just some projects that we have done related to the technology and applications. For example, the Lemon project, which I will introduce a little bit more detail related to Hanoi. The project related to the impacts of toll collection system in Ho Chi Minh City. How if we release the release the toll collection around the city, which the influence to the transportation system of the city. We also have done some parking management in MBC, which you can find it interesting because the MBC is very common in Vietnam. It is motorcycle dominated cities because we have a rather, typical traffic and transportation system. We also have tried to develop the bike-sharing system as the support for the public system in the city. Try to develop something related to the environment-friendly system for the transportation. We also have conducted some research related to the ITS for the expressway network in Vietnam. Now Vietnam have the problem of the ITS of the different corridor because we get the ODA project of different corridor of the expressway, and then we have the technology from like Japan or from Korea, which is a little bit conflict. And how to harmonize such kind of system is the problem of Vietnam now. We also work with the high-speed railway planning. Now it is still in the discussion in our government whether we can push it or not. Though Vietnam's geographical is very good for this one, but whether we need it now or not. Here are some detail for BRT, for example, where we try to develop the BRT system in Da Nang, which is a medium-sized city in the central of Vietnam. We also put the modeling and simulation software from Germany, which is called Visum, for this project. Here are some results for the project. Here is also from the same software, but in the micro level, which is Visum, and we try to develop the simulation for the traffic control in different sections. When we push the BRT into the practical. We also, here are some results from the software. We also have the Visum in the traffic control. Here is one bus station in Hanoi, which is which is rather complicated. And then we also do the analysis from different options to how to manage this segment at the entrance gate of the bus stations. Here are also another example of the design where when this is a very complicated intersection. We have 5 or 6 branches into this intersection, and then the government, Hanoi authority would like to build the flyover bridge here in this area. But when we are trying to do the modeling and simulation, we see that such kind of measurements can affect in the whole corridor, cannot solve for only one point. So the reason why we consult the Hanoi authority not to build this bridge here. We also work a little bit in related to the logistic area, which is more or less related to the multimodal transport. So it is just very brief introduction about our work. And here is one of the projects that I have mentioned above, which is a remote project, which we are trying to do something like real-time monitoring for the transport and traffic transport, just based on the GPS device on the system. We have the GPS signal from the bus, from the taxi, which is forced under the Vietnam regulations. And we also have signal from other, like motorcycle, because from the mobile phone. So in this, I will skip some slide here. But in this project, we use something we call floating car data. That means the GPS device or GPS signal from different vehicles can give you the information of the speed and so on. It will give you the quality of the traffic flow, so that you can see whether it is smooth running or it have some stuck or people have some traffic jam real time. So it is the idea of the project, and then here is the structure of the project, where we have the GPS from the vehicle come to the server, and then it comes to the map, and then it is displayed in the website or in the mobile phone in iOS or Android system. Here are some idea of this, and here are some examples. I will skip the structure of the system because it will take time. Here are some works that we have done. In fact, this one is the complicated system which we have the cooperation from Vietnam side and also from Germany side. But from UTC, we have we are responsible for comprehensive digital roadmap as well as points of interest. In this map, here are some work required for this project. Like firstly from the open source map, from the satellite image, and also we have the survey in the on spot to update related to the traffic control system of Hanoi, which is very complicated. And here are some work, and then we have here the results from the project, the street before the project, and then the updated one after the project with the traffic control, not only with the traffic signal, but also from one-way street or something like that, or related to the point of interest. Like, for example, we show that it is, you can see here the bank or the ATM or some restaurant, so on. Petrol station, and then it comes to the database of the system, and then you can see it from a very user-friendly interface in that way. And then after a while, we have the detailed comprehensive digital roadmap with attributes. We have we can suggest the routing or navigations for the driver if they need For example, because it related to the real-time situation, current situation status of the traffic flow. So, for example, you have 2 or 3 options to go to your target, but you can choose some more optimal related to the time traveling time, and so on. You also have the detailed points of interest to increase the value of the ads. That means provide more information for your user. And also in our project, we also developed the export system, which that means the real-time information can be stored in the server, and then it will be analyzed afterwards to see, for example, for different road segments, whether it is good or not for in history. And then we can give some, and also from this data for 3 years after the project, we also get the data to develop the simulation and to develop the traffic planning and management system for Hanoi. So it is, in fact, it is the final target, final objective of this project, not only monitoring one. And here is some image of the export system. And that's all what I would like to introduce about for today. Thank you.
Small question about the scale of the project. I mean the number of vehicles. That you get the data, get the information to know about the transport situation on site. That's the number of vehicles you get information.
Okay, in fact, it is we do not have the precise number of the vehicles. However, we get the signal from more than 1,000 buses in the bus system of Hanoi, or at least it is all vehicle fleet from the bus, and we have more than 6,000 taxi, which from taxi company. Only I remember that it is only for 6 big taxi group in Hanoi, and we also have some. I think that it is about some thousands of motorcycle, which is come from. Normally, it is from the. I don't know how to translate it into English, but it is taxi motorcycle. Yeah. And also it is from the delivery company, but it is also the motorcycle, because in Hanoi it is very typical. Hanoi have a very small road, a big number of small roads and alleys, so we cannot, taxi and bus is not enough, so we need from motorcycle.
So I ask some around 10,000.
So I want to talk about smart tourism. I think my talk is totally different from the previous talks. So my talk is related to virtual reality and augmented reality and mixed reality. So my major is computer vision and computer science, and so I think the topic is totally different. Anyways, so my interest is to introduce and like these technologies into the tourism and transportation. So we have been proposing the smart tourism framework. So we think we have 3D models of course the cultural heritage assets or water structures, and we want to use the 3D models for motivate to visit the local historical site, or we want to use the 3D models for navigation, and we want to use the 3D data for showing something, for example, the lost cultural heritage assets, and give the impression. And also we want to share the experience by using 3D data. And first I want to talk about the 3D modeling. So of course, if there is nothing, for example, this is an example of a Japanese temple, but this is now you cannot see this temple. So, but if we have a restored plan, we can make the CAD model. So this is a computer graphics model. So, and if we have physical things, real things, of course we can make the 3D model from the real object. So this is Nara, Great Buddha, very famous Buddha statues in Japan. And so this is actually the reconstructed, the original state of Nara Great Buddha. So we can use the 3D models of like these objects. And also we can make the 3D models of the urban structures. So for example, this is the city, and by using the 3D modeling techniques, we can get the 3D models like, this is actually point clouds, and we can get like these models. So for that, we are using the mobile mapping system, and the vehicle has a LiDAR and camera and the GPS, and also we can use the speed pulse, etc. So, but we are computer vision guys, and we are using the like these cameras and profiler. This is laser and sensor. So, and in this case, we didn't use the GPS and the GIAO. Just we used the cameras and the profiler data for estimating the motion of the vehicle. So this is a scheme of the profiler scanning. So the profiler can get just the sliced depth data. So then we need to estimate the motion of the sensor by using something. And so we use the panoramic images for estimating the motion of the camera. And also we have the depth data at the same time at 4 lines. And so then we use the depth data at the same time with camera tracking. And then, so this is an example of the scanning. So we wanted just the panoramic camera and the profiler like that. And then we could get the 3D models like this. Now we have the 3D models, and we want to use the 3D models for navigation. And so here we are using the augmented reality technology to enhance the driver's awareness. So for example, so this is a very foggy image, and the driver cannot see the vehicles and also the human beings. So that we can enhance the awareness by showing the like this object by using the augmented reality. So then this is called AR navigation. This is an example. So for example, when we are just passing through the road, and we can see where is the, this case, the power station, and which direction is the most effective way to get the destination without consuming the power battery. So this is actually one of the example of the AR navigation. So, and so these are the issues on AR navigation. So the issues geometric has a geometric aspect and a photometric aspect. Geometric aspect is just estimating the position and the pose of the vehicle. And a photometric aspect is visibility of the displayed object. So I will explain this one by one. So generally, for estimating the global position of the vehicle, we are using, of course, a GPS system. So when we use the GPS in the urban environment, of course, the accuracy is not so high. For example, in this case, when we use the GPS on the top of the roof, we can get very accurate positions. on the other hand, when we use the GPS just beside the buildings, the accuracy is very low. So even if we use a GPS and the inertial sensor, that is a very hard coupling sensor, of course we cannot avoid the accumulation of error if GPS cannot get a good position. So then we proposed a method to refine the GPS positioning by using the 3D data. Because we have 3D data of the urban environment. So then, at this time, we eliminated the multipass effect by checking the hidden satellites. So that means, so now we have like this 3D model, and we can make the like this image from the 3D model. So then, when we plot the position of the satellites, we can find that some satellites should be hidden by the buildings. So then we can eliminate like these satellites, and then we can get the correct position by using the actually clearly seen satellites. So this is actual position, and these are the positions by usual GPS positioning, and then this is our result. And another way to get the accurate position and the poses is image-based motion tracking using 3D data. So again, we have the 3D data of the environment. So we can use this 3D model for tracking the camera. So upper image is taken by the panel camera. This is the input. And the lower image is made by the 3D model. So now just we need to find the matching between the real image and the synthesized image. So this is, and the red one is the real image and the input image, and the white one is just render. So synthesized image by using the 3D data. So then, so when we make the synthesized image, we can know the position and the pose of the camera. So then, by matching these images, we can get the correct pose and the position of the camera. And also, at this time, we use the multiple panoramic cameras. And so when we use just one camera, most of the part are hidden by the vehicle itself. So then we use at this time 2 cameras and made a synthesized image, and then made a matching between the real image and the synthesized image. And this is an example, and this is just the input image, and we put the 3D object according to the estimated position and pose. I think you cannot find a difference between the real image and the 3D object. So that is the accuracy of the estimation of the pose and position is very accurate, very good. And this is the evaluation of the position and the pose estimation. And actually the position error is under 6 centimeters. And I think it's very accurate in the urban environment. And another issue is photometric aspect. That is the visibility of the displayed object. So currently there are many optical see-through head-mounted display and of course the head-up displays. But the problem is visibility changes according to the foreground object and the background scene. So for example, in the lower left image, we render the cube in front of the brick. And the cube can be seen, but when we move the cube in front of the glasses, and the cube cannot be seen. So this is caused by the difference difference in the visibility of the virtual object. So then, so our idea was just checking the visibility of the virtual object by using the visibility predictor. This is actually based on the human perception model. So when we render the virtual object on the real scene, we can predict the visibility of the virtual object. So then we can feedback this for rendering the object. So, and then we can get the clearly visible virtual object. So maybe I need to skip the detail, but so in the algorithm, we just first estimate the visibility of the background scene and also virtual object, and get the difference between them, and then this is used for render the virtual object. And this is a video. So when we use the uniform alpha branding, so in this case, the background is a flat textured object and the cube cannot be seen clearly. But when we use the visibility-based branding, the cube is clearly seen. The visibility is uniform over the virtual object. So that is when we look at something augmented object on the head-up display. The object is always seen uniformly and clearly. This is an example of the application to virtual reconstruction of the virtual heritage assets. On the left side is a uniform alpha branding, and the right one is the visibility-based branding. Okay, and so next I want to explain about the impression by mixed reality. So at the navigation part, I said augmented reality. Augmented reality is just augment the real scene by using the virtual object. But in this case, we use the term of the mixed reality. So because we want to actually mix the real scene and the virtual scene. So in this case, left one is actually photograph in the historical site in Japan. There is nothing. But when we, for example, we are the head-mounted display, we can see the like that temple. So this is called mixed reality. And this is an example. So there is nothing, and we can put the virtual object on the real scene. And then we can see the lost cultural heritage assets. So again, so we have two programs. One is registration. So we are to put the virtual object in the display. And another one is occlusion handling. So I think in the lower image, the virtual object is floating because the tree should be rendered in front of the virtual object. So this program is called occlusion handling. And I skipped the detail of the registration because it's really related to the estimation on the pose and the positions. So then, for example, left image is a synthesized image, and the right one is the input image. This is actually the same as I explained previously. So then I can use this registration method in mixed reality and also augmented reality. So then I skip the details. And this is depth perception in mixed reality. As I explained, so unfortunately we cannot estimate the depth of the scene. So then when we put the virtual object in the real scene, the something happened. So in the right image, the human beings are rendered behind the object. So then the virtual object looks floating. So then we need to render the virtual object behind the human. So this is very important for depth perception of the real scene and the virtual object. And this is so in this case the camera is fixed and the human is just walking in front of the camera. And so at this time we use the background subtraction based on the illumination invariant value, and we extracted the human, and also we estimate the direction of the sunlight, sun, and then we casted the shadow of the humans onto the virtual objects. Actually, this work was done by Vincent. He was from Vietnam. But so in the previous case, the object was very simple. But if the foreground object is complicated, it's really difficult to segment the foreground and the background. So then we developed another method to handle the occlusion just by rendering semi-transparently, rendering the virtual object semi-transparently. So that is, so in this case the virtual object is floating, right? But when we use semi-transparent rendering, we can put the object behind the tree. And this is again based on the human perception. When the contrast, so we need to check the contrast of the virtual object in the real scene. So our depth perception is based on like this X-junction model. So when we see the left side image, you can see the left square is in front of the right square. So this is based on the sequence of the contrast. So the intensity gradually changing like the C shape. So then we could see the left square is definitely in front of the right square. But the intensity changes like this shape, Z shape. We cannot recognize which one is front and the back side. So then we want to make the right side case by changing the transparency of the virtual object. And so I skipped the detail, but so we made a depth perception model, and so we just need to check the contrast between the P and the Q and the P. So that is virtual between the object and just the overlap area. And we have developed a blending method based on the intensity of the virtual object and the real scene. So let's skip the details. And so this is an example. So left one is simple alpha blending, and the right one is a proposed blending method. I'm sure you can see the difference, but so left one looks the virtual object is in front of the tree, and in the right case the virtual object is behind the tree. So even if we don't have a clear segmentation of the foreground and background, we can use our method like this. Now we are developing like this version handling method. We are using the semantic information. So now I think if you are image processing guys, you know what is semantic segmentation. So when we are given the image, we can segment the image into some labels. For example, the ground and the building or skies. So then for example, the ground and the sky should be the different background. And also sometimes the trees should be maybe see-through and semi-transparent. So we use like that semantic information for rendering the virtual object. And so when we have the image sequence, left upper image, we can get the semantic segmentation, and also we can get the depth image. So then we combine the depth and the semantic segmentation, and then get the probability map. And then we use this map for rendering the virtual object. And so this is an ongoing project. Left one is a semantic segmentation result, and so right upper side is our result. And so this is an example video. So if the virtual object is on the ground, that part should be clearly rendered. And if the object is behind the tree, that part should be see-through. And now we want to integrate the navigation part and the impression part. That is, so we want to combine the augmented reality and the mixed reality. And so our target is actually historical, local historical site. And so maybe you have the same problem, but we do not enter the big buses or the vehicles in the local historical areas. So then, so we want to use other transportation method. Of course, the walking tour is a very easy way. And then maybe we can use personal mobility vehicle, but it's very dangerous because the user needs to wear the head-mounted display. So then we developed this mixed reality mobility system. So when the users take the seats and wear the glasses, head-mounted display, they can see the virtual object while passing through the local historical areas. And I saw this car in Hanoi, and I think you can implement our system easily. Anyway, so our system is composed by the two panoramic cameras and the GPS, and have the client PCs and server PC, and the images are sent from the server PC to the client systems through the Wi-Fi. And so we are using two cameras to remove the hidden part by the areas by the vehicle itself. And the images are cut out according to the direction of the viewer direction. So this is an example. So we wanted to reconstruct the virtual scenes. So not only the just a small building, we wanted to reconstruct like this ancient capital. So then we made like that system. So this is actually demo scene. So all users we are in the head-mounted display, and you can see the actual background scene, real scene, and virtual object at the same time. So this is another example. So this video is seen on the northeast area damaged by tsunami. And so there is nothing after the tsunami. So, but so the people, they were living there, but they wanted to see the old town, a lost town. So then we reconstructed, not reconstructed, but we put the pictures of the this town before tsunami into the 3D world. And then we used this mixed reality system again to show in the reconstruct the lost town. So there is nothing, but when you pass through on the road, you can see the lost town by using the pictures that are put in the 3D space. Okay. And so now we are trying to automate the driving, not just automated driving system. We are using a human and robot because so when we use the automated vehicle, so just we can move. The human can move from some point to the destination. But so when we use the human and robot, we can use the human robot in the emergency place. So then we developed the teleoperation system of the human robot by using the virtual space. So the robot is actually in the emergency situation, and then the image is sent to the operator. So he's distant place from the emergency area. So then he moves in the virtual space, and then the robot moves again like the human moves. And so we use the Kinect and the deep motion to take the human motion. And then when he moves, the robot moves like his move. Okay, so then I want to summarize my talk. So we have proposed the smart tourism framework. So we want to use the 3D models for motivate to visit the historical site, and we use the 3D models for navigation and show the lost something, and also we want to use the 3D model for sharing the experience. Okay, thank you very much.
Kính thưa các vị đại biểu, kính thưa các nhà khoa học đến từ Nhật Bản và các nhà khoa học Việt Nam. Hôm nay tôi xin thay mặt nhóm nghiên cứu của Viện Ứng dụng Công nghệ giới thiệu với quý vị một số kết quả nghiên cứu của Viện Ứng dụng Công nghệ trong ứng dụng xử lý ảnh để giải quyết cái bài toán thu thập dữ liệu của dòng giao thông.
Yeah, ladies and gentlemen, there's a professor and the other expert in the meeting room. Today, on behalf of the research team of the National Center for Technological Progress, I would like to send to you the presentation about the camera image processing to collect and analyze the data, traffic data.
Bài giới thiệu của tôi thì gồm có 3 phần. Phần thứ nhất là một số cái kết quả nghiên cứu có liên quan trong và ngoài nước được nhóm nghiên cứu tham khảo. Phần thứ hai, các cái giải pháp thu thập dữ liệu giao thông bằng xử lý ảnh từ camera di động. Và phần thứ ba là ứng dụng mạng neuron tích chặt để nâng cao độ chính xác của hệ thống thu thập dữ liệu giao thông bằng xử lý ảnh.
The presentation includes 3 content. The first content is we will introduce to you some research in the domestic research and the foreign research about the ZIP field. The second, we would like to introduce to you the solution to collect the traffic information by image processing using the movable camera. And the third, we would like to introduce to you the application use neural network integration neural network to improve the accuracy level of the data collecting system by image processing.
Như quý vị đã thấy thì dòng giao thông ở Việt Nam nó khác so với các cái dòng giao thông ở các cái nước khác trên thế giới, ở chỗ là cái mật độ phương tiện rất là cao, trong đó thì xe máy là chiếm tỷ lệ chủ yếu, và cái tính tổ chức trong cái dòng giao thông nó không được cao như những cái nước mà có hệ thống giao thông phát triển. Thế thì cái bài toán thu thập dữ liệu bằng công nghệ xử lý ảnh thì đã được chúng tôi theo đuổi cũng khá là lâu, từ năm 2007 cho đến thời điểm hiện tại, thì các cái giải pháp cũng được hoàn thiện dần qua thời gian, từ chỗ là thu thập dữ liệu giao thông từ các cái camera cố định đặt trên đường, cho đến thu thập dữ liệu giao thông từ các cái camera di động mà chúng ta có thể lấy được hình ảnh qua các cái camera hành trình. Thì để giải quyết cái bài toán này thì chúng tôi cũng tham khảo một số các cái hệ thống trên thế giới, thì thấy rằng cái hướng nghiên cứu mà dùng camera di động cũng là một cái hướng được khá nhiều các cái nhà nghiên cứu quan tâm. Ở đây thì chúng ta có thể thấy một cái nghiên cứu của Đại học Cambridge của Anh, thì nghiên cứu cái ứng dụng cái xử lý ảnh để giải quyết cái bài toán phân vùng ảnh đường giao thông. Cái hệ thống phân vùng ảnh đường giao thông này nó có khả năng phân vùng đường giao thông thành các cái đối tượng và được biểu diễn bằng các cái màu khác nhau, ví dụ như là đường, xe cộ, vỉa hè, cây cối và các cái công trình hai bên đường.
Okay. Please. Please. I couldn't catch everything. Okay, as you know, the traffic situation in Vietnam, the traffic flow is dominated by the motorcycle. Then we couldn't apply directly the technology and other solutions from other country to Vietnam. From that solution, we just learn from the concept and the theory from other country to collect the traffic data. Use the camera as one solution, but by the way, we also propose to use mobility. How to say, movable camera? It's meaning camera can when the camera travel along the road, it also can collect the data and analyze that traffic data. From that proposal, we try to make the literature review and collect the knowledge and the information from other research in the world. And one of the research we refer to is the research from the University of Cambridge, UK, to analyze and collect the traffic data using some kind of algorithm for the real-time urban traffic management. You saw in the slide. Then with this algorithm and this solution, we use a traveling camera, but we can collect exactly and separate each kind of the objective and separate it, define it by the different color. That is the one algorithm we learned from the University of Cambridge.
Chúng tôi cũng tham khảo một số các cái công trình nghiên cứu về xe tự hành, thì chúng tôi thấy rằng trong các cái hệ thống được tích hợp trong xe tự hành thì nó có cái phần ứng dụng thị giác máy để phân tích hiện trạng giao thông xung quanh xe. Cái ứng dụng này, cái chức năng này cũng có thể được sử dụng cho cái việc thu thập dữ liệu giao thông, phục vụ cái việc chức năng quản lý điều hành giao thông.
We also refer to the model of the autonomous vehicle from the other country and other company, such as Google, and we saw that in each autonomous vehicle always have the one kind of the machine vision. With the machine vision, we and use that kind of the methodology, we can make some kind of the collecting system and analyzing system to collect all objective around the vehicle along the street.
Hai hệ thống xử lý ảnh tích hợp trong xe tự lái được chúng tôi tham khảo đấy là hệ thống xe tự lái của Google và hệ thống xe tự lái của Nvidia. Thì cái mà chúng tôi tham khảo ở đây là việc sử dụng mạng neuron tích trật để phân tích hình ảnh và từ đó đưa ra cái số liệu về cái trạng thái giao thông quanh xe.
Two system of the autonomous vehicle we are referring now is the system of the Google and the system from the Nvidia. And with this system we see we are using 3 cameras from left, right, and the middle. And we use algorithm from the CNN to make the image processing to decide the decision is a turn left or turn right or increase or decreasing the speed.
Các công trình nghiên cứu trong nước chúng tôi tham khảo thì cũng có thứ nhất là cái hệ thống được xây dựng từ năm 2007 của trường Đại học Giao thông Vận tải. Hệ thống này ứng dụng công nghệ xử lý ảnh để thu thập và giám sát quản lý trên đường cao tốc.
And for the domestic research we refer to for the system is one research we did in the 2007. The traffic monitoring system for the expressway. We use camera to monitor the traffic system, traffic situation on the expressway.
Hệ thống xử lý ảnh thứ hai mà chúng tôi có tham khảo trong cái công trình nghiên cứu này, đấy là cái hệ thống xử lý ảnh phục vụ cho giám sát và quản lý trong giao thông đô thị. Hệ thống này thì được Viện ứng dụng công nghệ phát triển từ năm 2014 và hệ thống này có khả năng tính toán mật độ trung bình của dòng xe, tính diện tích đường của xe chiếm dụng và tính tốc độ trung bình của dòng xe. Khác với hệ thống giám sát đường cao tốc thì cái hệ thống giám sát giao thông trong đô thị này có cái mô hình phân tán.
And the second system we are referring now is one research of the NACETEC we did in 2014. This system can detect the average density of the traffic flow, the area of the pavement occupied by the vehicle, and the average speed of the traffic flow. And the difference between this system and the system on the expressway is on the expressway this system is a distribution model, analyzing distribution model of the system.
Sau khi nghiên cứu, sau khi tìm hiểu về những cái công trình có liên quan thì chúng tôi rút ra một cái kết luận là thứ nhất cái ứng dụng xử lý ảnh để thu thập dữ liệu giao thông hết sức phù hợp trong cái điều kiện giao thông Việt Nam. Thứ hai là các cái kết quả nghiên cứu trước đây tại Việt Nam thì chủ yếu là sử dụng giao thông, sử dụng camera tĩnh đặt cố định ở một vị trí. Trong cái nghiên cứu này thì chúng tôi hướng đến cái việc sử dụng camera di động.
And from the literature review, we have the conclusion that the first, the image processing application to collect the traffic information in Vietnam is very suitable with the mixed traffic flow in Vietnam. And the second is the research result now in Vietnam almost using the fixed or the stable camera, but we would like to use the other kind is a movable or movable camera.
Yêu cầu chung của cái bài toán xử lý ảnh ở đây thì nó xuất phát từ các cái thông tin cơ bản nhất của ảnh, đấy là các cái pixel, sau đó thì đến các cái đặc trưng cao hơn, ở mức cao hơn, ví dụ như cạnh và cái hình thái học, rồi có thể đến các cái đặc trưng cao cấp hơn như là cái hình dạng của khuôn mặt chẳng hạn. Thế thì
The most important requirement for the image processing is we need to consider about the characteristic of the each pixel, such as the characteristic of the shape of the pixel or size of the pixel or other thing. Or sometimes such as with the complicated situations, such as to detect the face, we also need to detect the characteristic of the face or the shape of the face or something.
Xử lý ảnh từ camera di động nó có những cái khó khăn hơn hẳn so với xử lý ảnh từ camera cố định. Ở cái chỗ cái ảnh mà thu được từ camera di động thì nó có rất nhiều cái hiệu ứng, trong đó thì có hiệu ứng quay, có giãn, biến đổi cường độ sáng và biến đổi trạng thái của đối tượng trong ảnh. Thế thì để giải quyết cái vấn đề này thì chúng tôi phải tìm ra các cái giải pháp, các cái đặc trưng trên ảnh để nó bất biến với các cái phép biến đổi như trên.
To compare between the image processing between the stable camera and the movable camera, we need to consider too many changing and many changing in the sum factor of the movable camera, such as rotating or scaling or illumination or some kind of the transition of the objective inside the picture. And to detect and analyze and make the processing of the camera on the movable camera, we need to define some fixed or some unchanged character or some unchanged factor, and from the unchanged factor we continue to estimate and analyze for the other factor.
Một trong những cái đặc trưng mà chúng tôi sử dụng trong bài toán thu thập dữ liệu bằng xử lý ảnh đấy là đặc trưng highlight. Thế như chúng ta đã biết thì cái đặc trưng highlight này được sử dụng khá là phổ biến trong các cái máy ảnh hiện đại. Họ sử dụng cái đặc trưng này để phát hiện các cái khuôn mặt khi mà chúng ta chụp ảnh. Trong cái nghiên cứu của chúng tôi thì chúng tôi cũng đã sử dụng cái đặc trưng highlight này để phát hiện các cái đối tượng là xe, người đi xe máy và ô tô trên cơ sở các cái đặc trưng là cảnh, là đặc trưng đường, đặc trưng điểm.
One of the most important algorithm we are using is a highlight feature, highlight character. With the highlight character, is using now to detect the face, but based on that methodology, we also can detect many other kinds of the objective or incident with the traffic image, such as road or side or pavement or some other objective.
Chúng tôi sử dụng cái đặc trưng highlight này để phát hiện người đi xe máy, đây là xe máy, và phát hiện ô tô trên cơ sở là huấn luyện cái chương trình xử lý ảnh, tìm ra các cái đặc trưng highlight cảnh, đường, điểm trên ảnh.
We also use highlight characteristic to detect and to counting the vehicle based on the recognizing the face and detect the car and the vehicle, and training for the machine to learn how to detect the face, how to detect the vehicle based on the data set.
Tiếp theo chúng tôi sử dụng đặc trưng LBP. Cái đặc trưng này được sử dụng trên cơ sở là so sánh cái cường độ sáng của một điểm ảnh với các cái điểm lân cận.
The second algorithm we use, the second methodology we use is a LBP character to detect the pixel by style based on the illumination level of the pixel.
Đặc trưng này được chúng tôi sử dụng để phát hiện cái biển số xe trong giám sát các cái đối tượng vi phạm giao thông.
This character we use to detect and recognize the license plate for the 8 vehicle to make the monitoring for the traffic flow.
Đặc trưng tiếp theo chúng tôi sử dụng là đặc trưng HOP. Đặc trưng này thì được sử dụng chủ yếu để phát hiện người đi bộ trên đường.
The next characteristic we use is a HOP, histogram of the oriented gradient. This characteristic is used to detect the pedestrian on the streets.
Sau khi sử dụng các cái đặc trưng này thì chúng tôi có cái nhận xét là việc sử dụng các cái đặc trưng nêu trên thì nó cho độ chính xác khá cao trong cái điều kiện là mật độ giao thông bình thường, nhưng khi mật độ giao thông cao và ảnh của phương tiện xe bị che khuất một phần thì cái độ chính xác sẽ giảm xuống rất nhiều.
After the conclusion of the implementing is after we try and implement the characteristic to recognize the traffic flow and traffic data, we saw the result is okay and good in the good condition of the traffic flow and the average not so high traffic density. But in case of the very high traffic density, then the model and the character have a lot of the mistake and the failure when have many vehicle cover other vehicle. Then it's very difficult to detect the different level of the vehicle.
Từ những cái nhận xét trên thì chúng tôi mong muốn là tìm được các cái giải pháp để nâng cao cái độ chính xác của cái bài toán thu thập dữ liệu giao thông bằng sức gạt. Thì chúng tôi tìm được cái công cụ ở đây gọi là mạng neuron tích chậm và thấy rằng cái công cụ này có khả năng giải quyết cái bài toán thu thập dữ liệu giao thông với độ chính xác khá là cao.
From our analysis, then we saw and we found out one solution to resolve the mistake and the failure with a former characteristic algorithm. We change to a convolutional neural network (CNN) algorithm to increase the accuracy level of our algorithm.
Tôi xin phép bỏ qua một số các cái slide có tính kỹ thuật.
Sorry, he will pass some technical slide to the next slide.
Như tôi đã trình bày ở các cái slide trước thì cái giải pháp của chúng tôi sử dụng đấy là sử dụng mạng neuron tích chậm để thu thập nâng cao độ chính xác của bài toán thu thập dữ liệu dòng giao thông. Ở đây mạng neuron tích chậm chính là cái công cụ được sử dụng trong cái mô hình sắc nét mà tôi đã nêu ở phần đầu để phân vùng ảnh giao thông theo thời gian thực. Thì trong nghiên cứu chúng tôi cũng đã sử dụng cái mô hình này để áp dụng cho cái điều kiện giao thông Việt Nam, và mục đích của cái mô hình này, mục đích sử dụng cái mô hình này chúng tôi là đo lường cái mật độ xe chiếm dụng trên mặt đường.
As the first part of this presentation, we saw to you that we use a SegNet model to detect the traffic information and traffic vehicle, and when we use the CNNS charter, we can detect we can apply it on the SegNet model to detect the moving objective on the traffic flow in Vietnam.
Xin phép bỏ qua cái slide này. Ngoài mô hình sắc nét, chúng tôi cũng sử dụng mô hình có tên là Faster CNN để phát hiện và đếm và phân loại xe lưu thông trên đường.
Besides the SegNet model, we also use the Faster CNN model to detect the vehicle and motorcycle on the road.
Cái clip này là chúng tôi sử dụng mô hình Faster CNN để đo, phân loại, đếm và phân loại xe với cái hình ảnh thu thập được từ camera cố định.
This clip showed to you one sample. We use a Faster CNN model to detect and counting and analyzing the traffic situation from the fixed from the stable fixed camera.
Như quý vị thấy thì cái kết quả phát hiện và phân loại xe đã sử dụng cái mô hình phát CNN độ chính xác khá là cao.
And from the result you saw on the video, we can see the result we get from the faster CNN model is a little high. Accuracy level is high.
Ở bước tiếp theo thì chúng tôi sử dụng cái mô hình CNN này để xử lý ảnh từ camera di động.
In the next, we will try to implement the CNN model for the movable camera or traveling camera.
Trên màn hình là cái kết quả sử dụng mô hình CNN.
This video is show to you, the clip show to you the one very interesting result when we use the traveling camera to detect the vehicle on inside the traffic flow.
Trên đây là tôi vừa giới thiệu vắn tắt cái kết quả nghiên cứu của nhóm công nghệ thông tin trong việc ứng dụng công nghệ áp dụng kỹ thuật xử lý ảnh để thu thập dữ liệu dòng giao thông. Hy vọng với cái giải pháp này kết hợp với các cái giải pháp khác phục vụ cái việc thu thập dữ liệu giao thông thì chúng ta có thể thu thập được nhiều dữ liệu giao thông với độ chính xác cao phục vụ cái bài toán quản lý điều hành giao thông. Vâng, tôi xin hết.
And as a part and as in the content in this presentation, I already introduced to you the research result of the IT group in the NASCENTEC to research the solution to monitor and counting and analyzing the traffic flow by the traveling camera. And I hope this solution also this application.
So I am Shintaro from the University of Tokyo. So today, let me introduce my brief introduction of general review of my research topics, and in the latter half of this presentation, let me introduce the topic entitled the subtitle of this title. Okay. My research interests include sensing and modeling and space-time video analysis and driving simulation and so on, and its application to the intelligent transport systems. And let me firstly introduce this mobile sensing vehicle. So by using this kind of vehicle, or sometimes using laser scanner on top of the roof of this vehicle, or if the vehicle is stationary, and by repeating the scanning, we can construct this kind of very precise 3D model of this kind of very complex road structure. And this is a video of the road structure, a double group in the metropolitan expressway of Tokyo. You see that the 3D structure and also the reflectance value of the 3D model. And by constructing this 3D model, you can simulate arbitrary viewpoint or cells lighting simulation or acoustic simulation and so on. And in another case, we can construct very, very long tunnel, 3D model, very, very long tunnel, which is actually the part of the Tome expressway, whose length is 4.6 km. And at the time, yes, this is what it looks like. This is a set of 3D points. And at the time, since we cannot use GPS inside the tunnel, we apply this kind of 3D to 3D matching technique. Stitching to stitching, and at both ends of the side, also with waiting on the feature point on the surface of the tunnel. And at both ends of the tunnel, west side and east side, the absolute coordinate is fixed by using a very precise GPS. And then after that, we can fix the model as right figure shows, and then create this kind of very long 3D structure with as this video shows. Yes, it continues 5 minutes or so. Okay. And also we tried to stabilize this. We also tried 2D video data. So this is the example of stabilizing the 2D video, and yes, 2D video. So this is input, this is input, and this is output. As you see, this the video is stabilized. In this case, we perform this kind of point tracking as this figure shows. You will see that the red line is very vibrated in the top view, and the red line is very smooth in the bottom view, bottom picture. So in this case, we performed point tracking as this video shows, and then performed a so-called structure promotion technique, and constructed very rough, very sparse 3D model, and as this the white line shows the trajectory of the camera. So this is a so-called structure promotion technique in the field of image processing. And then we applied we virtually recreate a straight smooth camera trajectory, and then we output the new viewpoint, new pose, and then we can create this stabilized view. Also, recently we have tried the super resolution of a video captured by on-vehicle camera. So this is the input is very low quality image, and the output is a very fine image, and the low quality image is collected by a general vehicle. I will introduce the detail about this topic in the latter half of this presentation. And after the modeling of the real scene, the next interest is understanding of real scene and also information extraction from the real scene. So in this topic, we took advantage of so-called space-time image. So space-time image is corresponding to the video. So you will see the video frame 1, 2, 3, 4. And then by arranging each video frame in the third axis as a temporal axis, you can get this kind of volume, which is called space-time volume. So by cutting or by interpolating this kind some part of inside this kind of volume, it becomes possible to make some application by such as finding or removing some foreground object or so on. I will show the example. So this is a very clear example. So the left one is input video, and the right one is the output video. So we could remove the foreground object from the observed scene. Yes, we have separated the foreground part and the background part. How could we do that? Okay? In this case, we first make a space-time volume from this input image and cut the horizontal surface, and then you will see this kind of some strange image. This is called space-time image. So it is composed in a very short explanation. It is composed of a set of one-line image. So simply extracting this one line from the first frame, which is corresponding here, in the second frame and third frame. So temporal axis is this direction. And after correcting the speed, it becomes look like that, as if the background object is stopped. And then by completing the color in the temporal direction, we can remove the foreground object. And by applying this kind of operation in every height, cutting height for the input image, we can output this kind of result. And in some more complex cases, even if the foreground background is hidden by this kind of very complex object, somehow in some time slot, all the background is visible. In some part and in some time slot, it is visible. So by accumulating some visible information like this, and it becomes possible to extract the background. To tell the truth, we set the assumption that the background structure is planar in this case. And also, in this kind of some more free motion video, it becomes possible. Yes, at that time, also we assume that the background structure is planar, so we can know the motion of the video, motion of the video camera, and after that we can remove the foreground also. And in some other cases, I have also tried the parking vehicle recognition. At that time we use laser lens scanner, and laser lens scanner is used for extracting the side surface of the parking vehicle, and also we applied classification, automatic classification of the street parking vehicle in 4 types. And next interest after the understanding or information extraction from the real thing is association of data to data or else complementing of the data each other. So for example, in this case, the input is 2 types, so real image sequence of street image sequence, and another input is a 3D distance, very simple, not very fine. Just a very simple set of rectangle, set of cube type digital map. So this input does not have 3D information, and also this input does not have color information. And then by finding building to building correspondence through this kind of at that time I use height information as a cube for matching, and then find building to building correspondence and add a color onto this surface of this map. And we perform same kind of thing, same kind of way for not only for color, photo, video to 3D map, and also laser lens fine 3D data to 3D map. So rough 3D data to really simple 3D data, and find building to building correspondence, and add really very precise precise 3D structure onto the surface of the 3D map. And also this is a case of 2D video to 2D video matching. So this is a kind of searching. So we assume that we already have a set of video data captured in some area, or in this case it is some area of the area, and with its 360-degree street view in advance. And in other opportunity by other vehicle, when the vehicle pass through some street of the area, and then the searching query input is a video sequence, and also matching result coming is answered from the database. Oh, this video is corresponding to this frame, from this frame to from this frame of this video. At that time, we also used height information, finding that the border between sky and building, and so on, some temporary information and some color information. We could succeed to know the correspondence of video to video. So this is a success case. In the failure case, the most failure case is the case when it includes very complex tree and leaf structure. It doesn't work very well. And also in the night also. And another story is the application of real-time processing, including practical use, and so on. So this is the story of driving simulator. Maybe you will know this kind of this kind of view, looking at a set of computer graphics. So this, is the driving simulator very popular in Vietnam? I'm not sure, but maybe in Japan this kind of driving simulator is quite popular for driving lessons and so on. But as you know, this is very composed of a set of polygon models, and which with poor reality compared to current computer graphics, computer games, and so on. And it costs huge for model construction, but almost all conventional driving simulator is realized with this kind of rendering technique. So what we propose is, on the other hand, to use this kind of video captured by on-vehicle camera, and then use this kind of very very rich photo reality, and at the same time less human cost for model construction. And yes, we do not use only as a video image, but also as a conventional computer graphics model. Also, we use two types. One is this part is for background thing, this part is for foreground thing. So this is because it is very difficult to embed or synthesize other vehicles by real image processing, or else to get rid of other vehicles what that was captured when the capturing vehicle runs. So such kind of operation is not very easy in the real image. So we still use computer graphics model for road surface and traffic signals and traffic signals and so on. Yes, traffic signals and signals is a second reason. There is a need to change the traffic signal or to change the traffic signal in the experiment, not just looking like the real scene, but the scene that is different from the real scene can be a purpose of driving simulation experiment. So there is a need for such kind of. Yes, this is an example, very simple example how to realize lane changing effect of the lane changing effect using real video. So by cutting and stitching array of the capturing vehicle, it was possible to show the lane changing effect. And also we applied data compression technique. So since this kind of view has a very large redundancy, so it is viewed from so many directions, and it is looking like very similar. So it is possible to apply principal component analysis, and then we apply this kind of data compression technique. And also we applied semi-automatic modeling of road structure, not only by scanning and modeling from reality, but also using the national GIS data that is provided by the ministry, and then we use such kind of data for road surface modeling. And then this is looking for the video-based driving simulator, and it looks the video looks like this. You will see that there is a very high photoreality here, the reflection of the light on the glass surface of the building. And then we are applying this kind of technique for driving simulation for disaster prevention, using this kind of video captured into our area. And then yes, we went to the area and collected this kind of data. Then this is an example, very simple example of real driving simulation here. This is a disaster affected area. So in the latter half of this presentation, let me introduce the super resolution on-vehicle wide-angle fisheye videos. So the general background of this topic is looking like this. Today, cars have become a kind of distributed sensors and connected sensors, meaning that the telematics, and it is applied for autonomous driving and also intelligent parking and so on. So by combining this kind of technique with on-vehicle camera, it might become possible to apply this kind of technique for map making or also anti-crime security by taking advantage of some image collected by individual vehicles. So these are the example of cameras, on-vehicle cameras that become very popular, including driving recorder or parking assistance camera and so on. So this is a comparison of sensing by special vehicle or sensing by general vehicle. Although the data quality capture collected by special vehicle is very high, and it is possible to set very free specification when you design this kind of special vehicle. It requires very high cost, and also there is a difficulty for frequent sensing in wide area, especially for rural area. But on the other hand, by sensing by general vehicle, although the data quality is low, the data quality of position or image quality is very low, it exists so many data exists. So there is a possibility of improving quality through post processing. So this is the topic of this one. So here purpose is to develop a super resolution method for on-vehicle videos for its low resolution and quality. And another important assumption here is we use wide angle or fisheye camera here. This is because we assume the practical case. So in the commercially sold vehicles, it is not reasonable to the user to buy to cost more by attaching additional camera. So please pay more when you buy a car. So it is not reasonable. So in that case, it is often super wide angle camera or fisheye camera is often used because it can capture very wide area by using just one camera and less cameras and wider field of view. So that is why wide angle camera is often used for on-vehicle camera. So by this assumption, we try the super resolution here. So in technical speaking, what we have to do is dealing with dynamic distortion and also adaptive model is needed. What does this mean is represented in this slide. So idea of super resolution is very simple. Like this animation shows when on-vehicle camera captures one thing and then on-vehicle camera proceeds and capture another image frame, it becomes possible to increase the resolution if you can very precisely align the image one by one. It becomes possible to increase the resolution. And yes, in order to do that, we have to formulate the degradation model, how this ideal image is degraded into this kind of low resolution image, and it is observed. We have to formulate this downsampling or displacement or blur or noise effect. It is possible to formulate this kind of degradation process. Yes, this is a known fact. This is a known fact. The degradation model is already proposed. But here, what is difficult, what is challenging in this part is the use of wide angle and fisheye image. So when the target area, for example here, when the target area is captured in the very peripheral area of the site, in the vehicle proceeds, it is captured here, and it is again captured in the peripheral area of the site. And then, of course, it includes very huge distortion and blur in the peripheral area of the site. And then it means that when the camera moves, the appearance changes, and deformation and blur, depending on the position, region is a region existing in the site. And here, the displacement is not represented as simple parallel translation. So as I have shown in the former slide, like this very simple animation, it does not true in this case. So we have to develop this some kind of adaptive model in this case. So yes, maybe we modify this degradation model. So we apply deformation and apply image alignment in the stage of input stage. So this is the modified observation, and then this we have ideal image here, and then it is degraded without image displacement, only blur, and also with additional scaling. And then by comparing these two images, and if it is looking very same as the original image is the truth as an answer. Okay, so the lens distortion can be simply performed by using existing tools, and it is possible to get this kind of image. And also image initial alignment is performed by image-to-image block matching. And then after image-to-image block matching, graph matching, we performed very precise fine matching by using by finding a correspondence between one frame to another frame. This is a correspondence of self key point, and then applied homography conversion. Homography conversion is a technique often used to change the viewpoint when it can be regarded the object is almost blurred. So in this example, if we can apply this this area, it becomes possible to look at this intersection with top view. This is a homographic approach. And then we developed a new degradation model. So maybe I will skip the fine mechanisms of this part, but I have so set this mechanism, including lens blur or defocus blur and synthesized blur and its scaling and so on. So blur is expressed by deformer Gaussian kernel, and also how to estimate the size of the blur can be realized by from the observation of the image. So in the ideal case, it can be seen as a step function, but actually it is seen observed as a Gaussian function. And so by fitting a Gaussian curve, and then we can know the size of the blur and so on. So let me skip a little bit, but the scale of the blur can be also estimated from the input image observation. And after the experiment, so in this is an indoor experiment, and this is an outdoor experiment. We performed capturing by one-week camera, and then this is the result. So this is with homography transformation and our adaptive blur model. It shows that from this very low quality image input, it becomes possible to get this high quality image. Maybe you can read the character of these characters on the side. Maybe, and by comparing the method without our adaptive model, it seems worse in this case. So this is not yet. So our new challenge is to find optimal trade-off in input images, meaning that in this case, using very super wide angle camera, so less image, high quality with less image, or more and more images, including worse quality. This is a concept, you know. So since the vehicle is passing in front of the object, so the good quality image is captured in front of the object, and but less number of images. So if you want many images, it includes the image with worse quality. So which is better? We don't know at this time. So now we are trying to find the optimal point, optimal condition, which image to get rid of, or which image to join to the superimposition process. This is our current challenge. So yes, this is the end of my presentation, including these topics. Thank you.
THØNG as a professor, lecturer, associate, assistant professor of Kusakabe, and Professor Edward from the Queensland University of Technology. Those two I invited from outside of Japan, our center, and also outside from Vietnam. And also I like to say very appreciation from the UTC side participation, and also support from NASETEC. And so at this moment, as you see, we made one memorandum of the understandings among our university and UTC and NASETEC. So maybe for the future, we will collaborate for our more progressive outputs we hope to have. And therefore, I think today's this event may be something a cue to start our collaborations. All right, so that's my brief address. And again, I'd like to say thank you for all your participation.
Thay mặt trường Đại học Vận tải xin cảm ơn các giáo sư bên trường đại học Tokyo. Tôi biết rằng trường đại học tổng hợp Tokyo là một trường rất lớn ở trên thế giới, và rất là hân hạnh trường đại học công vận tải có một cái sự hợp tác đối với cả các giáo sư của trường. Xin trân trọng cảm ơn.